So, we continue with our discussion on binary decision diagrams. If you recall, in our last lecture, we said what a binary decision diagram is. We also talked about something called ordered BDD, ordered binary decision diagram, where the order in which we are expanding the variables, that is fixed from or with respect to any path from the route that we follow. Let us say if I use an order A, B, C, so we will be expanding along all the paths in that same order A, B and C. Now, in this next lecture on binary decision diagrams, we shall be talking about some rules using which you can reduce the size of the BDD, because as I said, the size of the BDD as such is exponential in nature, because the number of leaf nodes, the terminal nodes, that will be equal to 2 to the power n, the same size as the output column of the truth table. So, we have to do something to reduce the size, because exponential is a really large number. Suppose I have a 20 variable function, how much is 2 to the power 20? 2 to the power 20 is 1 million. A 30 variable function, how much is 2 to the power 30? It is 1 billion. So, that number grows very rapidly with n, all right. Today, we talk about functions with 100 variables and even more. So, we just cannot represent a binary decision diagram in the conventional way. We need some rules for reduction. Let us see. So, a reduced ordered BDD, that is what we call, this is referred to as ROBDD. Well, we know what is a binary decision diagram. If the ordering of the variables is constant along all the paths, we call it ordered BDD. Now, we apply some rules to reduce the size. So, what we get is reduced ordered BDD. So, we have this reduced ordered BDD, where two reduction rules are applied systematically. These are the two rules we shall be illustrating. We shall be merging any isomorphic subgraphs. What is isomorphic subgraphs? Isomorphic subgraphs are two graphs which are identical in nature. Like, let me take an example. Suppose I have a part of my BDD which looks like this. There is another part of my BDD where also the same structure is found. So, I say that these two are isomorphic. So, if I find two such subgraphs which are identical or isomorphic, we can merge them into one. This is one rule, and we can eliminate any node whose two children are isomorphic. So, what I mean is that suppose I have a decision node B at a higher level. So, one of whose children is pointing here, other is pointing here. So, what I say is that both are pointing to basically the same thing, right? These two indicate the same thing. So, there is no need for using B. So, if B is 0, then also we will be doing this. If B is 1, then also we will be doing this. So, we can simply eliminate B from this graph. This is the so called elimination rule. We shall be seeing this in more detail. Now, the interesting thing about ROBDD is that it is a canonical form. Now, you recall when we talked about sum of product and product of sum representations, we talked about canonical representations. Canonical is some sort of unique representation. This reduced order binary decision diagram with respect to a particular variable ordering is canonical, which means there exists a single unique ROBDD representation. Okay. Now, because there is exactly one ROBDD for a given function, this is a very useful property using which we can use it in many applications. One such application is functional equivalence checking. Like, we have two functions f1 and f2 and we are not very sure whether they are the same function or not. We want to check whether they are equivalent or not. So, what you can do? We can create the ROBDD of the two functions and then check whether the two ROBDDs are identical or not. Okay? Fine. So, some properties of ROBDD, as I have just now said, there are two main properties. One is uniqueness. No two distinct nodes can be labeled with the same variable name and have same low and high successor. Just the example that we took earlier, A 01, the same example let me show once more, and again A 0 and 1. You see, let us say this is my node u and this is my node v. It says that you cannot have two such nodes u and v labeled with the same variable here A and have the same low and high successor. Low successor is 0 in both the cases and high successor is 1 in both the cases. So, if you have such, then you will be merging them into one. There will be unique copy of such structure existing, and non-redundant is the other one. It says no variable node can have identical low and high successor. So, a particular node cannot have, let us say, both the dotted and the solid arcs pointing to the same node in the next level. This means that A is not required. So, irrespective of the value of A, you will come to B anyway. Okay. These are the two main properties of ROBDD that needs to be satisfied. So, this is explained diagrammatically here. First is the reduction rule, where we say that if we find isomorphic subgraphs, merge them. So, two cases are shown here. There can be similar cases, other similar cases also. If you find that there are two subgraphs like this, two nodes labeled with the same variable x and x, same low and high successors child y z y z, then you merge and you see they are coming from two different places. Okay. So, then you merge them into a single node and the two different places from where they are coming. So, now there will be two incoming input edges, one from this one, other from this one, but you use a single copy of this, Similarly, this edge may be solid, this edge may be dotted also. So, and this is the other example. So, if you have this thing, then you can merge this like in this way, same way, merge these two and the two edges will be coming like this. So, you can have the other cases also. I have not shown all, like for example, one of them can be dotted and the other can be solid. So, in that case when you merge, the first one will be dotted and this one will be solid, right, or the other way around, this one solid, this one dotted. Okay. So, you can have all such cases of merging. The other case is to remove the redundant nodes, like I already mentioned this. So, if you have a scenario like this, where there is a decision node labeled with x, it says if x equal to 0, you come here, if x equal to 1, come here. Now, you see this decision does not make any sense, because you are anyway coming to y in both the cases. So, it says you can altogether eliminate this node x and get a reduced representation like this. So, these two rules, if you apply repeatedly on a binary decision diagram, then the size of the BDD will be going on reducing step by step, and finally, we shall be getting a representation which is called the ROBDD, or the reduced order BDD representation of the function. Let us take an example, complete example for constructing the reduced order BDD. So, we consider a 3 variable function like this, a function of 3 variables. Okay. So, if you use the method for constructing BDD that we discussed earlier, you have the function here. Let us say I expand the variables in this order, first x 1, then x 2, then x 3. So, I am not showing the steps, you can use this expansion step to get the functional representation. So, I am only showing the final one. So, once you do this, the BDD you get will look like this. This is your initial form, non-reduced version of the BDD, right. Now, you see you will be applying those two rules that I mentioned in a repetitive fashion. You will be merging nodes whose left and right childs or low and high childs are identical, or if you get isomorphic subgraphs, merge them. Now, with respect to the original BDD, one observation you can immediately see that in the terminal part there are so many 0 and so many 1 nodes. So, why not merge all the 0 nodes into 1 and why not merge all the 1 nodes into 1? That is the first step you do. Okay. So, you see here in this example there are 1, 2, 3 0 nodes and 5 1 nodes. So, the first step we do is something like this. We use a single copy of the 0 node and a single copy of the 1 node. You see the 0 nodes were pointed from where? The dotted edge from x 3, you see from x 3 dotted edge still comes here, dotted edge from this x 3 still comes here, this x 3 also comes here, and also from here this also comes, no, this 3 only. Okay. And the 1, the right, the solid arrow from x 3, the solid arrow from x 3 is coming here, the solid arrow from the x 3 also, solid arrow from this x 3, solid arrow, and both dotted and solid arrow from this x 3, right. So, this is the first step of reduction. Now, in this step you can make some observations. Well, the first thing is that you see if you look at this part x 3, both the dotted and the solid edges are pointing to the same node. So, as far as our reduction rule we can eliminate x 3, and another thing also you see if you look at, just look at these two nodes, this x 3 and this x 3. You see these are isomorphic. Why? Because in this x 3 the low child points to 0 and high child points to 1. Here also low child points to 0, high child points to 1. So, they can be merged. So, after this reduction step we get something like this. You see exactly what I said, this x 3 was having 2 parallel edges pointing to 1. So, here we have eliminated that x 3. This x 2 is now with a 1 edge is directly pointing to 1, x 2 is directly pointing to 1, and these two x 3s have been merged into 1. This is the x 3, and the input edges you see, one was coming from x 2 the dotted line and the solid line. Now, from x 2 both the dotted line and the solid lines are now pointing to x 3, right. So, after this reductions we get this. Now, in this version you see now again we have a scope for reduction. You look at this part of the graph, this x 2 has both the dotted and the solid arrows pointing to the same node. So, x 2 can be eliminated. Okay. So, you get finally after eliminating x 2 a BDD like this. So, you can understand what is the purpose of carrying out this reduction. because in the original BDD there are 8 terminal nodes in the lowest level, 8, 4, 12, 14, 15, total 15 nodes, and after reducing you are left with only 5 nodes. For larger function the reduction can be even more. This is the basic purpose of carrying out reduction and getting a ROBDD. So, what you get finally here, this is your ROBDD for this particular variable ordering that you had used x 1, x 2, x 3. But if you use some other variable ordering, then you can get some other structure for ROBDD. Okay? Fine. So, some benefits of ROBDD are pretty straightforward to understand. You see, you have a function f. Now, I want to check if the function is equal to 1 for all assignments of input variables. Such a function is called a tautology. Now, for a BDD, it is very easy to check whether a function is tautology, because the ROBDD of that function will simply be like this. It will straight away point to the node 1, right, not only dot, also dash. So, checking for tautology is simple, f will be pointing directly to 1. The second thing is that complementation. Well, you look at the, okay, let us take an example BDD and trying to illustrate. Suppose I have a BDD representation, let us say I have x 1, I have x 2, I have x 3 here, and I have 0 here, and I have 1 here. Let us say x points to like this. Suppose I have a function like this, this is f. Now, what I am saying is that suppose I have a BDD of a function f, now I want to get or generate a BDD for the complement function. Should I have to go through the process again and construct the BDD? It says it is not required. If you have the BDD for a function f, just interchange 0 and 1, make this 0 as 1, make this 1 as 0. So, for all those cases where the function was getting the value 0, now it will get the value 1, and for all cases where it was getting 1, now it will get 0, just the reverse, right. And thirdly, this equivalence, whether two functions are identical or not, it is easy, because here you have seen that ROBDD is canonical. So, if you construct the ROBDD of the two function and show that they are the same, then you can say that the two functions are equivalent, or otherwise the functions are not equivalent. Okay. Now, you means you can use this ROBDDs in various ways for synthesizing circuits also. So, we shall be taking some examples. Say earlier I mentioned that the 2 to 1 multiplexer, the way we designed a function using such multiplexers, and the way we realize a BDD, implement a BDD using repeated Shannon decomposition, they are very similar. So, a BDD node and a 2 to 1 multiplexer, they have a 1 to 1 correspondence. Let us take some examples. So, in synthesis, what I mean to say is that you see some of the reduction rules that we are applying, we already mentioned that. One is this rule, where if a node is pointing both edges to the same node, I can eliminate that node. Well, in terms of switching algebra, what does that mean? You see, if this entire subfunction below, this represents a subfunction h, then this BDD represents x bar h or x h, the left hand side. So, if you take h common, it will be x or x bar, which is equal to 1, it gets eliminated, only h. So, this kind of a algebraic minimization is implicitly carried out during this transformation. Similarly, the other one, there are two identical or isomorphic subgraphs, suppose they represent H. This means A H plus B H. So, if I merge them like this, it means A or B and H, they also are the same. So, again using some rules of the switching algebra, we do this kind of minimization. So, we are doing the same thing implicitly using this graphical data structure of BDD. So, let us make one point here. This already we have mentioned that variable ordering can reduce the size of the BDD. Okay. Now, this variable reordering is also one way to minimize the logic implementation implicitly. So, we are not talking or thinking about gates, circuits, minimizing, we are thinking about the function, the BDD representation. We are trying to find out what kind of variable ordering can give us a BDD which is smaller. Now, a smaller BDD may mean a smaller circuit. So, we are thinking about a correspondence like that. Okay. And during the construction of the BDD itself, as we had seen, some redundancy are implicitly removed. So, the idea is that when we use a BDD, we are already carrying out some minimization, function minimization, while we are constructing the BDD, while we are applying the reduction and merging rules to get the ROBDD, we are already applying some minimization, right. Okay. Now, let us talk about the multiplexer realization of functions. You think of a scenario like this, a decision node in a BDD labeled x, its low child represents a function f, the high child represents the function g. Now, if I want to implement this decision node by a multiplexer, well, a multiplexer symbolically is sometimes denoted like this, like a trapezium. This is your select line, this is your multiplexer select line, this is your multiplexer output, and this side are the inputs. And 0 1 indicates if x equal to 0, which is selected, f is selected, x equal to 1, g is selected. So, this is exactly what the decision node means. If x is 0, you come this side, if x is 1, you come this side. So, this can be directly mapped to a multiplexer, and you can repeatedly do this. This f and g can be further decomposed, you can have more multiplexers generated for f and g. Okay. Fine. Let us consider some scenario like this. Well, you have two sub functions f and g. Well, I am showing some segments of BDD, and you can have a decision block here which can be represented by h. It means, if some condition h is true, then you go to h, g, if h is false, then you come to f. That means, if h is 0, then f, if h is 1, then g. Now, if we have a scenario like this, if you can identify this h, then you can again realize this using a multiplexer where the select line is generated from h, because depending on h equal to 0 or 1, you will be selecting either f or g. If it is 0, f is selected, if it is 1, g is selected, right. Let us look at a concrete example here. Consider a scenario like this, where you can say this part indicates h and this is our C and D are our means inputs. So, you can have a multiplexer like this, C can be fed to one side, D can be fed to the other side, and this H, whatever it is, this H network, this can be used as the select line. So, you can have a mapping for the multiplexer realization like this. Okay. Let us work out a complete mapping example with respect to the BDD that we had taken as example earlier. This was the ROBDD that we had generated from the function. Now, what we want to know now is that let us have a complete multiplexer based implementation for this function. So, how do we do this? We start from the root side. Let us take x 1. We take one multiplexer here. The output of the multiplexer generates the function f. The select line is connected to x 1. Now, there are two 0 and 1. Now, we will be having two inputs here. One is for select line 0, other is for select line 1. Let us show them like this. Now, if it is select line 0, where do you go? You come to here x 3. So, there will be another multiplexer out here. This will be selected by x 3. So, again there will be a 0 input and a 1 input, and for x 3 the 0 input is connected to 0 and the 1 input is connected to 1. So, you can directly connect it to 0, you can directly connect it to 1. But for the other case here you have x 2. So, here you have a multiplexer which will be selected by x 2 and the 0th input will be connected to x 3. So, this one. So, x 3 node is indicated by this. So, this same thing will go here 0 input and the 1 input is connected to 1. So, 1 input is connected to 1. So, you see this BDD using a pure multiplexer realization, you can have something like this. But of course, one thing you understand that this may not be the best possible realization. For example, if you look at this part, what does this function mean? X 3 in the select line 0 here or 1 here, it means if x 3 is 0, you send 0, if x 3 is 1, you send 1. This is as good as x 3. You can eliminate this multiplexer and you can directly connect x 3 here. Okay? So, such minimizations are possible, but in general for a large BDD, for every decision node you can directly map them into a 2 to 1 multiplexer. So, this is a very convenient and easy way to map a BDD to a multiplexer network. This is one of the ways in which synthesis of circuits using multiplexer kind of a network can be carried out. Okay. So, to summarize, we have talked about BDDs. Now, BDDs has many applications. They have been traditionally used to represent and manipulate switching functions or Boolean functions in many ways. They are used to generate circuits which are called synthesis. They are used to verify the operations of circuits. There is a branch called formal verification where they are very heavily used, and there are many software packages which are available already in the internet which you can download and use for manipulation of BDDs. So, you can create a BDD for a function, you can minimize them in various ways. You can do given two BDDs, you can find the AND of the two BDDs, or you can complement a BDD. Lot of such operations can be carried out. These are all supported by the BDD tools. So, with this we come to the end of this lecture. So, over the last couple of lectures we talked about binary decision diagram. which is a very important data structure that is used to represent and manipulate switching functions. Thank you.